All right, so in this part we would like to talk about frequency spectra. So frequency spectra can be used to identify what kind of frequencies are present in a given signal. So for example, you're putting a hot wire or you're recording the signal from your computation for a single point. You're getting then a signal that, let's say, looks like this. So you have the velocity u, and as a function of time. And now you suspect that there's a dominant frequency within this signal already. And if you look closely, I mean, you could expect there's something like a sine curve over here. So there's a frequency already present in the flow. And that is being obscured by the turbulence, by the stochastic and the random turbulence. So you would like to pick out, you would like to know how much of that frequency is in there. And what is the frequency? What is the frequency of this signal? And that is actually something that happens quite often. And quite often you don't really see that like here. It's just somewhere hidden because the turbulence is obscuring the frequency signal even more. So essentially, a frequency spectrum would be splitting up the signal into its frequency components. Splits up a signal into its frequency content. Okay, so what is it that we want? Oops. What we want is something like a function where we have here, for example, the energy content of a given frequency, and here the frequency. So we would like to convert our original signal into this domain, and then let's say a typical energy frequency spectrum might be looking, for example, like this. And then you see here at this point, you have a dominant frequency. So, but of course, not all turbulent signal will have a dominant frequency, but if you can read an energy spectrum like this, you see a peak here, then you know, well, at this frequency of 1, let's say, we have a dominant frequency, so there's something we need to do about that. All right, so how do we get that? So we need to derive some mathematical tools that can get from this signal to this over here. And so we need to have something like a spectral representation of a signal. And first we will consider a periodic signal. Okay, so we're going to derive that for a periodic signal, and we're going to go about the implications about that a bit later. But if the signal is periodic, then for example the velocity u, or any quantity t plus capital N t is equal u of t. Okay, where n is an integer, or possible integer. And capital T is the wavelength, or the periods of the signal. So essentially the signal is periodic, so after some time it's going to repeat itself. Essentially that's what this says. All right, so the time average then. Originally we need to average over the entire time until infinity, but here we just need to average over u of t over one period, because it repeats itself. And then 1 over t, integral from 0 to t, ut dt. And but then you have the fluctuation part, the fluctuating part, lowercase u is equal uppercase u minus the average, of course. And of course, that is equal to the average of the fluctuating part is then going to be 0. Okay, what else do we need? We need the frequency. We define that omega n equal 2 pi n over t. So for n is an integer number, so you can have as many as you want. And the Fourier mode that corresponds to that, it's the nth complex Fourier mode. So that e to the power I omega n t. If I write that out, cosine omega n t plus I sine omega n t. I can put this one inside, then I get cosine 2 pi n over t times t plus I sine 2 pi n over t. Okay, so essentially every frequency within any given frequency, the nth frequency, you can now define or express with this expression. Okay, a bit more to that a bit later. If you're not getting it right now, just give me one more moment. I'll explain it one more time in a second. Okay, so then u as a function of t can be expressed as a Fourier series. U of t is the sum over n equal minus infinity to plus infinity, an plus I en e to the power I omega n t. All right, so this one is essentially what we had over here already. So this one is essentially a frequency, and now your original signal, you can now split it up into, or you can express it as a superposition of a large number of frequencies. And each frequency, so you have here an infinite number of frequencies from minus infinity to plus infinity. You have factors that are essentially describing how much of that frequency is within your signal. And essentially, I'm rewriting now this original signal as a superposition of all of these frequencies, and depending on an and bn, how strong these frequencies are, you can, well, if they're 0, then, for example, that frequency is not present. but you can have anything else in between to any kind of amplitude that adds up to it. And I hope you're going to get the principle now. So if you're now be able to express or determine now these constants here, a n and b n, then it tells you already if, for example, a n is very large, that this frequency is going to be very large within your original signal. With that, you're going to have a large dominant frequency. Okay, but to get to that, we need to do a few more things. First of all, can also rewrite this one here as the following. The sum of n equal minus infinity to plus infinity Cn. So Cn is now a complex number, e to the power I omega n t. And here, so an and bn are real numbers, and Cn is a complex number. Okay, so I can now express this one here in terms of cosine and sine. And I have u of t is sum minus infinity plus infinity an plus ibn cosine omega nt plus I sine omega nt. All right, I'm going to rewrite that the following way. U of t is equal to the sum from n equal 1 to infinity. So I'm not counting from minus infinity to plus infinity. an, okay, I'm leaving some space here. I will see in a moment why. Plus I bn, again some space, cosine omega t plus, okay, so essentially I'm just rewriting this term over here. But I'm counting only from, instead of counting from minus infinity to plus infinity, I'm counting only from 1 to infinity. So since cosine of t is equal to cosine of minus t, I can just count in the other direction as well. So I can just add here plus a minus n, and here plus b minus n. To take into account all of the ones that are counting from minus infinity to plus infinity. Then, so we have taken care of this term. We need to take care of the other term here as well. So then we count from n equal 1 to infinity. And so I have then here I times an. Then I leave some space, plus it's I square, sorry. So we have here I times I. So this one becomes then minus over there. Just a second. And we have here bn, again some space, sine omega t. So in sense here, sine t is equal minus sine of minus t. I need to keep the minus over here. So that's an minus I, sorry, a minus n minus b minus n. All right, there's something called conjugate symmetry. That says that an is equal a minus n, and bn is equal minus b minus n. So if an is equal minus an, then this one becomes 2an. bn is equal minus bn, then this term here becomes 0. an minus an, these are the same, this one becomes 0. And this one becomes 2bn. We see that all the imaginary part, this one here, and this one becomes 0, 0. This one we can write out as minus 1. We are left with the following. U of t is equal to sum of n equal 1 to infinity an cosine omega nt minus bn sine omega nt. Alright, so you have now rewritten your original signal in terms of cosine and sine, and now we need to have a and bn, and a and bn is essentially containing all the information how much of this frequency is going to be present inside this flow. So we have so an and bn hold the information on how much of a particular frequency is present in the signal. U of t. Alright, so we can write it here in terms of an and bn. We can also write it in a little bit different form. U of t is 2 times the sum of n equal 1 to infinity. Cn, the absolute value of Cn cosine omega nt plus theta n. Both are essentially identical. Once you write in an and bn and cosine and sine, here cosine, if you shift cosine, for example, if your theta n is pi half, then cosine becomes sine again. So essentially, you're just rewriting it in a little bit different form. With Cn is then going to be the square root of an squared plus bn squared. So that's the absolute value. And theta n is the tangents, arctangents of bn over a. Okay, this has the advantage that you have now here a value for the amplitude directly and the phase shift. So, and in the previous form, they are somewhat hidden at the phase shift depending on how strong bn is compared to an. Here you have written it out. You have here the amplitude directly and the phase shift, and that helps it, makes it a bit easier to analyze. In particular, the amplitude is something that is quite important to understand. All right. Now we need to determine these coefficients. So these are very useful to analyze the flow, to determine now the coefficients an and bn or cn and theta n. But how do we get them? Okay, so how do we get them? The following way. To obtain the Fourier coefficients. We start with u of t is equal to the sum n equal minus infinity to plus infinity, Cn e to the power I omega nt. Okay, so this one is the original description. So what we do now, we're going to multiply another frequency against it, and then we're going to take an average. So we multiply with e to the power I omega mt. So this is the nth mode, and then average. So on the left side we have then e to the power I omega mt u of t, the average over it, and that is equal to the sum of n equal minus infinity to plus infinity Cn e to the power I omega nt times e to the power minus I omega mt, and the average of it. Alright, so it can be shown that e to the power I omega nt times e to the minus I omega mt average is the Kronecker symbol Nm because of orthogonality. So I can plot now delta or Kronecker Nm over here. So from that follows e to the power I omega t, u of t is equal to the sum of n equal minus infinity to plus infinity Cn Kronecker Nm. These two you can draw together because Kronecker Nm is only 1 when n is equal to m. Everything else is 0. So this one becomes Cn. And then I can replace again. So you see all of the n's are falling out here. So I'm just going to replace m with n. Again, then it follows that my Cn is equal to the average of u of t e to the power minus I omega nt. So I can calculate now my coefficients with this formula. I have my original signal. I have I multiply that with that corresponding frequency and do a time average out of it. It's essentially, if you look at you can look at that a different way. If this one is your original or the frequency that you would like to analyze at that point, so that's the nth frequency, you multiply that with the original signal. This is essentially an autocorrelation or cross-correlation. It's a correlation between the frequency that you would like to analyze with your original signal, the average. There's essentially a correlation on that. That's a different way to look at that. So if this one is a correlation here, essentially, you can also rewrite now the energy in the following way. I'm not going to go too much into detail here, but if I now say that the energy associated with the frequency E of omega is 2 over pi integral from 0 to infinity rs cosine omega s dx with rs equal u of t times u of t plus s. This is the autocovariance. So essentially you're not only looking at the energy spectrum, the spectrum itself, but you would like to know something about the energy associated to it. So from that follows that E of 0, for example, is going to be u squared. There's the energy associated to it. So if you're having now your energy spectrum, function of the frequency, maybe looks like this. And this value over there gives you the mean value of the energy. So this energy spectrum provides you with a physical interpretation of that frequency spectrum. Energy spectrum. And the interesting part here is that the energy spectrum you can also use to recreate the original signal. So the conversion from the original signal to the energy spectrum and vice versa. Or if you, for example, take this one here, you can now calculate your coefficients from your original, your frequency, from your frequency spectrum. You can calculate that from your original signal. But of course, if you go back over here, you can also recreate your signal from the coefficients. And the same thing, you can do that with the energy spectrum here. So the energy spectrum can be used to recreate signal. For example, Rs would be then here, you go from 0 to infinity, E of omega cosine omega s t omega. So there's no information loss. Due to that. All right, so now you know how to, you have the mathematical background to split up now a signal into its frequency content, and using a Fourier analysis. Using this one, you can have a look at the energy that is associated to each of these frequencies, and that in itself is already very powerful too. But there are some practical issues with that, and I want to go to that in a moment here. So practical issues.